Hello all. Today's topic is design of an asynchronous sequential circuit. The problem is design an asynchronous sequential circuit with two inputs x and y, one output z. Whenever y is 1, input x is transferred to z, that is z is equal to x. When y is 0, the output does not change, that is z does not change for any change in x. So the problem, what is given? Two inputs x and y, one output z. And what are the steps that you have to follow to solve it? Number 1, draw the flow diagram. Next, state diagram. Next, the primitive flow table. And then reduced primitive flow table. And then the K-maps. At the last, it is the implementation, that is the logic diagram of this asynchronous sequential circuit. To start with, first we should do the flow diagram. So this is the flow diagram that I am going to explain now. To study the flow diagram, what is given in the problem, we have to just revise it. So I have given it as a note in the side of the board. If y is equal to 1, z is equal to x. If y is equal to 0, z is equal to previous output. Why have I given it as previous output? It is given in the problem. Z does not change if the input y is equal to 0. What does it mean if the output z does not change? It means it is going to stay in the previous output. It will not show any remarkable change. Okay, so with this thought, we will start the flow diagram. So initially the inputs x, y are 0, 0 and the output is 0. So that is the initial condition. So how to make the next states? A transition is recommended. How to do that? I have given it in one of the points. It is C. A state transition with one bit change only can occur. So the 0, 0 can transit to two states. What are they? 0, 1 and 1, 0. And only one bit can change in the two given bits. X and Y are 0, 0. Only one bit transition can occur. So a state of 1, 1 is not possible. Okay. So 0, 1, 1, 0. Here you can observe there is only one bit transition. So that is what is your B and C. I will tell you at the end how to mark the states inside the bubbles. So first we will see the state transition and the inputs and the outputs, how to write them. So now the new states are 0, 1, that is x is 0, y is equal to 1. Outputs we have to write now from the given problem statement. And then the other state is 1, 0. So when coming to the B state, when x equal to 0 and y is equal to 1, what is going to be the output? Look into your problem which I have cut short and have written it here. When y is equal to 1, z is equal to x. So z is that denominator. So here x is 0, y is 1. So when y is 1, z is equal to x. What is x? It is 0. So you write it in the denominator 0. Now you know for a value of x equal to 0, y is equal to 1. What is the value of output z? It is 0. Similarly, coming to this state, here x equal to 1, y is equal to 0. So what is going to be the output? Look into the problem statement. When y is equal to 0, z is equal to the previous output. What is the previous output here? It is in the A state, that is 0. So for a value of x equal to 1, y is equal to 0, the output z is 0. It is the previous state output, that is 0. Okay. Now coming to the B, that is your state 0, 1 by 0. You can make again transitions. Here one more thing you have to observe. What is that one? Look into this note. B the point if any state already exists, it cannot be partitioned into new states. So before you make this transition to new states, you have to look into the previous states if it already exists. What is the already existing state? To start with, it is only 0, 0. So 0, 1 is a new state. It doesn't exist already. So now a transition of 1 bit can occur from this B state very easily. So 0, 1 can make a transition to, that is a 1 bit transition to 0, 0 and 1, 1. A single bit transition only can occur, which I have given in the note. Now again you have to find out the output. So when y is equal to 0, the z is the output is the previous output. What is the previous output? That is in the B state, it is 0. So you write this new state A as 0, 0 by 0. And then come to the next one, 1, 1. For D, it is the D. What is the y value? It is 1. When y is equal to 1, the z is going to be the x value. What is x? Here x is also 1. So 1, 1 by 1 is the next newly formed state. Similarly, come to this C, 1, 0. Is it already there? No. The already existing state is only 0, 0 by 0. There is no other state like 1, 0 by 0. Then the C also can make a transition to two new states. What are the two new states? Only 1 bit transition is allowed. So 1, 0 becomes 0, 0 and the other state is 1, 1. So how do you write the output? Look into the A state. When y is equal to 0, z, the output is the previous output. What is the previous output? That is the output in the C state above it. So it is 0. And what is the output for the D state? Y is equal to 1. Then x is also 1. So z is equal to x. It is 1. And then this again, look into this state. In this state, you should be you should not get confused. In what way? See, you have this 0, 0 by 0 already exists on the top. Okay, so 0, 0 by 0 cannot make transition to new states again because it had already formed its new states to B and C. So now here D, 1 by 1 is already not there. So it can cause transition to new states. So 1, 1 can be partitioned or can make transition to 0, 1, 1, 0. Again, how do you write the outputs? When y is equal to 1, z is equal to x. So x is 0 here. So the B state is 0, 1 by 0. Then again the next one, y is equal to 0, z is equal to the previous output. That is the output of the D state. It is 1. Okay. Now here, if you look into the adjacent states, the left hand side it is AD and in the right hand side also it is AD. So we have A is already existing there, we don't partition. D now we had partitioned, transition had taken place to B and E. So now again this right hand side A and D should not be further made to cause a transition. A is already there. D we had done here in the left hand side and made it to B and E. So leave it off as such. Now coming to B, that is 0, 1, 0. 0, 1, 0 is it also already exists. The second 11 you can see there. So that also cannot be made to transit to new states. Then coming to E. 1, 0 by 1, does it already exist? No. 1, 0 by 0 is there, but 1, 0 by 1 is not there. So you can make it cause transitions, that is only 1 bit transition. So it becomes 1, 1 and 0, 0. Now similarly write the outputs. For D, when y is equal to 1, z is equal to x. So x is 1, so it is 1. Coming to the F state, x is equal to 0, y is equal to 0. Whenever y equal to 0, z is the previous output, that is the output of the state E, that is 1. Okay. Now D, 1 by 1 already exists. You can see in the third level. Okay. So don't make a transition from the D state. Now F state, 0 0 by 1 is not already there. Only 0 0 by 0 is present in the previous levels. So 0 0 by 1 can make a transition to 0 1 and 1 0. 1 bit transition only is made possible. So here y is equal to 1, x equal to 0. When y is equal to 1, z, the output in the denominator, is equal to x value. The x is 0, so it is a 0. And for the next one, x equal to 1, E state, x equal to 1 and y is equal to 0. When y is equal to 0, the previous output is our z. So the previous output is from the F state, that is 1, that we have written here. Okay. So now 0 1 by 0 is already available, that is your B state, and 1 0 by 1, 1 0 by 1, that is also already available. You can see here which level, 1, 2, 3, 4th level. So furthermore, any transition cannot take place because both these states 0 1 by 0, 1 0 by 1 is already present. Now how to name these states as A, B, C, D, I'll tell you. The first one, it is a new state, 0 by 0 by 0 is A. And next two are also new states, 0 1 by 0, 1 0 by 0. So you call it as B, C. You can call it this side B, that side C, no problem. Then, but you should follow the same numbering, alphabetical numbering when you come down. And then again you meet in the third level, 0 0 by 0. It already exists. So give the same name A. Don't give a new alphabet. And then 1 1 by 1 is new. So next new state is going to be after C, it is D. So do that. And then 0 0 by 0 is already there. Name it A. 1 by 1 is already there. Give the same old name D. Then again B is already there. Then 1 0 by 1 is a new state. So after D, it is going to be E. Then 1 1 by 1 is already there. What name is given there in the third level? For 1 1 by 1, it is 1. It is D. So write that here, repeat it here. And then 0 0 by 1, it's not already there. So it is a new state. Give it a new name. After E, it is F. Follow the order. Otherwise, we will be in trouble for the next step when we do the primitive flow table. And then from F, B and E, it already exists. B is already there, E is already there. So because this B and E is already there, we come to a conclusion that no new transition is possible. So now the flow diagram gets over. The next step, we will see it in the primitive flow table. In the state diagram, I have given a small write-up for your understanding before we draw it. The state diagram is a pictorial representation of behavior of sequential circuits. The state diagram gives us the clear information about transition of states from the present state to the next state and also the outputs for a corresponding input. Each state is represented inside a bubble. You can see there A, B, C, D, E, F, all of them are given inside bubbles. The output is written inside each bubble. So the A bar slash 0, B slash 0, the zeros represent the outputs. So with this theory, we enter into the pictorial representation and it is done from the flow diagram. So the flow diagram, the first state is A. I have already told you how to name the alphabets and the alphabet should be given in the bubbles. So the A state is 0 0 by 0. So write the outputs inside the state. So A by 0 and the A state, it stays in which values x, y, 0, 0. So it is a stable state. A is stable for the state 0, 0. So put a self loop. that is it is stable for the value 0 0. Okay, so the inputs are written in the loop, outputs are written inside the bubble. From A it goes to B and C. So from A take it to B. You can see here it is going from A to B. So what is the output of B? You can see here it is 0. So B/0. And from A it goes to B, for which value 0 1 are the inputs, the transition. So 0 1, write it here. And next from A it goes to C. You can see here for value 1 0. From A it goes to C for the value 1 0. For C, what is the output? You can see here it is 1 0 by 0. So write it C by 0. And which state of C it is stable, value of C it is stable, C is stable for value 1 0, B is stable for value 0 1. So write that as self loops. C for 1 0, put a self loop. B is stable for 0 1. Okay, now we have to see from B and C, where does it go? From B it moves to A and D. You can see here from B it moves to A. You can see here it moves to A. For values, what are the values? 0 0. So write a 0 0 here. Output 0 will be already there inside A. Okay, so you get the same 0 there. So it shows that what you are doing is right. It will never change. Okay, if you do follow the proper steps. And then from B it goes to D. You can see here. Next it is a new state. So you are drawing a new bubble, and what is the output in D state? You can see here it is 1. So take the 1 and write inside the bubble. And for D it is stable for 1 1. Put a self loop for D. Okay, from B now it moves to A and D. A it is already I have explained. D it's a new state for the value 1 1. Okay, you can check the self loop is 1 1. D is stable for 1 1. B moves to D for the value 1 1. So write that here. Okay, and then what is the next one? From C it moves to A and D. So C already it is there. It moves to A for the value 1 0. The transition value is 1 0. And then from C it moves to D. So D is also already there. 1 1 it moves to D. You can see here from C to D that new state is 1 1. Okay, and next it's going to be from D. Have you seen B and E? Okay, so we are in this step now. From D it makes a transition to B and E. So B is already available. From D it moves to B. You can see here, and it is 0 1, that newly transitioned formed status. And then it moves to E. You can see here E is 1 0. So 1 0. And what is the self loop for E? Stable state. It stays stable. E stays stable in 1 0. So put a self loop 1 0. Okay, and then from E it moves to D and F. So from E it moves to D for the value, you can see here, for the value 1 1. And it moves to F, that is a new state. So new state, what is the value? For F it is 0 0. So it moves to F for the value 0 0. So F is stable for what value? 0 0. So it is a stable state. Put a self loop 0 0. The F output is 1. And then E. E is completed with E, D and F, that is done. From F we have to see now. What are the newly transition states from F? It is B and E. So from F it moves to B for a value 0 1, new status. And then from F it moves to E. You can see this line, that is the next state 1 0. Okay, so totally this is the way to do the state diagram. It is done clearly and thoroughly from the flow diagram. The next step is the primitive flow table. the primitive flow table is done from the state diagram. So the state diagram tells us that there are states from A to F. Those are the present states. So the primitive flow table has present state, next state, output. These are the columns. So write the present states A to F in the primitive flow table. And the next state, output. There are two things to be specified for a set of inputs. What are the inputs? The inputs given in the problem are X and Y, and the output is Z. So we have to here find out the next state for the set of the next state and the output for the set of inputs XY. XY are two inputs, so it takes the integral powers of 2. 2 power 2 is 4 combination we have. So write the 4 combination of inputs 0, 0, 0, 1, 1, 1, 1, 0. So why have I written it as 0, 0, 0, 1, 1, 1 and 1, 0? I have written it in the order of 1 bit change. 0, 0, 1 bit change, it is 0, 1. When one another bit changes, it is 1, 1. And from that, if only 1 bit changes, it is 1, 0. So we have to write in that order that we write it in the K map. Okay. So now, then from the states, look into the state diagram from the state A, where does it transit to? The transition takes place to B, that is 0, 1, and another transition to C, that is 1, 0. So come over here, find out for the input 0, 1. Okay, from A it moves to B and the transition state, new state is 0, next state is 0, 1. So write it in 0, 1, B. Okay, so B, comma, what is the next one? You should write here the output. Okay, two things should be written in each column. For each input combination 0, 0, 0, 1, 1, 1, 1, 0, we should write two things, next state, comma, output. So B, comma, what is the output written inside B? 0. But we should not write here 0, we should put a dash. Why, I will tell you. Okay, so before that I will tell you what is the self loop. That then you will understand why we give a dash in the other places. In if A, the self loop is 0, 0. That is the only stable state is 0, 0. The only stable state is 0, 0. So write it as A, comma, the output 0. Okay. So only for the stable state the output should be written. For all the other states a dash should be given. So it goes to B. We have seen 0, 1 is the next state. We have in 0, 1 we have written B, comma, dash, because it is considered to be an unstable state. And from A it moves to C for 1, 0. So C, comma, dash, you write it in 1, 0. And there is no transition to 1, 1 from A. You can notice. So you have to put the next state also as dash, comma, dash in 1, 1. Okay. So a state can transit to only two new states and one self state, that is stable state. So for each state there will be one stable state, that is the self loop, and two other next states. Only for the stable state you will write the output. For the other states you will not be writing the output. And then from notice from B. From B it moves to D, and then it moves to what is the other state? One is D, the other one is A. So from B it moves to A. What is the value of A? It moves to 0, 0. So write in 0, 0 A, comma, what is the output? You should not write the output as it is an unstable state. So A, comma, dash. Okay. Only the self loop you should fill it up. 0, 1 is the stable state. Come into 1, 0, 1, B. Okay. Adjacent to B, B, comma, 0. The stable state is 0. And then it moves to D, I told you earlier. So where is D? Yes, 1, 1. So in 1, 1, write D, comma, dash. So the three things are full. One is the self loop, that is b comma 0, the stable state. The other two are unstable states. Only 3 is possible. The other one is naturally going to be a dash comma dash. Now come into C. From C, it moves into A for 0, 0. So in 0, 0, you write a comma dash because that is an unstable state. What is this other state? It moves to D for 1, 1 from C. So from C it moves to D for 1, 1. Under 1, 1 you can write D comma dash. What is the self loop for C? It is 1, 0 and the output is 0. So come into the 1, 0, C comma, write the output 0 because it is a stable state. In this way you fill the whole thing. Now I think you understand. You want me to say it for anything else? Let me do it for F. Only E I am leaving it for you. So the F, the self loop is 0, 0. So in 0, 0 you can write F comma, the output 1. From F it goes to B, okay, for the value 0, 1. So under 0, 1, B comma dash. And then it moves to E for 1, 0, E comma dash, okay. It is an unstable state. And naturally the fourth one is a dash dash, okay. So a state can move into only two other states, and one, when it moves to itself, it is a stable state. The other two transitions it is making is an unstable state. Okay, so I have given you the notes for this primitive flow table here. What I have explained you in this table, I have given it as notes for your reference. Let me read it one more time for you. Each row has only one stable state. As I told you, in the first row, A is the stable state. Next for B is the stable state. It is a self loop, so you can find it out easily. So therefore it's called a primitive flow table. Next, the inputs are xy, so we have 2 power 2 is equal to 4 combinations of input. That also we know. Next, the inputs are written in the order of 1 bit change, 0, 0, 0, 1, 1, 1, 1, 0. And the fourth one, the output should be written only if the state is stable. That's what I remind you one more time. For A, the stable state, it is 0, 0 for inputs. So we have written the output as 0. For B, it is in 0, 1. We have written B comma 0. That is the only stable state. For C, the stable state is for the input 1, 0. So we have written C comma 0. And for D, the stable state, it's for the inputs 1, 1. So D comma 1 we have written in that column, and so on. So this is the way the output should be written. Next, fifth one, output should not be written when it moves from one state to another, as it is said to be unstable. So the transition to other states, for that we have put a dash. We have not given the outputs, considering them to be unstable states. And the last, sixth point, if 2 bits change, next state and output are marked dash. Both are marked dash for 1, 1 in A. Why? It is a 2-bit change. What is the A in A? It is in 0, 0. So A is stable in 0, 0. If it transits or causes a transition to 1, 1, then it is going to be a 2-bit change. We have already have the concept that only 1-bit transition is allowed. So when it makes a 2-bit transition, we don't take it into consideration. We put a dash comma dash. So this is all about the primitive flow table. So this is the reduced primitive flow table, which is framed from the primitive flow table, that is the previous step. Okay, so the title itself tells us that the previous step has to be reduced, shrunk. So how do you do that? I have given the notes here. Totally 6 states you can see from A to F are present in the primitive flow table, the previous step. So next step is to reduce the number of possible states. So the outputs are either 0 or 1. So divide them into 2 groups. You can see here the outputs are only 0 and 1. Okay. So we should divide them into 2 groups. How to do that? A, B, C is taken as one group. D, E, F is taken as another group. Why and how? See, for A the output is 0, B the output is 0, C the output is 0. So commonly the output is 0. So combine A, B, C together and assign them 0 and another state S naught. Okay. And what about the D, E, F? For D the output is 1, E it is 1. For F also the output is 1. So combine D, E and F into another group and assign them a value of 1 and a new state S1. So now we have A, B, C as values 0 assigned to them and a new state S naught. Okay. So thus one group is formed. The other group D, E, F is assigned value 1 and the state is S1. The other group is formed. So now we have two states S0 and S1 and we have the next state and output written in this form. How? We know for A, B, C the outputs are 0, D, E, F the outputs are 1. Having this in mind, come to the previous step. You can see here A, B, C it is S0. Okay. So for A, B, C we have written here S0. For D, E, F we have written S1. Okay. You can see both of them together in this coverage. So when for the first input 0, 0, A, comma 0, you write it there. For 0, 1, which is the steady state, write only the steady states. Okay. For S0 state, which is the steady state for the input 0, 0, A, comma 0. For 0, 1, it is B, comma 0. For 1, 1, there is no steady state in that column if you see. So you write, what can you write? For 1, 1, you write D, comma dash. Okay. D, comma 1, you cannot write it. That is a steady state value with output 1. So you cannot write that in 0. Okay. S0, you cannot write that. So D, comma dash. That is the one unstable state. We are writing that because we don't have a steady state in 1, 1. Next it is C, comma 0. Write that in 1, 0. Okay. Then coming to S1, D, E, F are replaced or assigned with S1. In that, look into the steady state. For 0, 0 it is F1. Write it there. And then 0, 1 it is, there is no steady state with an output 1. So write B, comma dash. You cannot write B, comma 0 because it is already written in the first state S0. And then for D, 1, 1 column of input, look into that, we have D, comma 1. For 1, 0 column, we have E, comma 1. So this is the way you form the reduced primitive flow table. And now here, next step will be the K-map. For that, you have to change a small, make a small change into this table and then go for your realization. From the reduced primitive flow table, we make small changes in order to do the K-maps. I have given here the notes for K-maps. The K-maps cannot be made from the above table, that is the reduced primitive flow table, because of the presence of alphabets A, B, C, D, E, F, S0, S1. So we assign the values to the alphabets S0, S1. The alphabets A, B, C is given 0, that we have seen already for making of this reduced primitive flow table. D, E, F as 1 also we have already done. S0 is assigned as 0 now and S1 is assigned 1. So now when you fill it up, you get this table in this form. Okay. This is the new form of the reduced primitive flow table with which we are going to work out the K-maps. If you see here, S0 is 1. I'll show you both the tables together. You can compare. S0 is 1 in the present state, S1 is 1. And then A, B, C are replaced with 0. You can see here, first column, second column and the fourth column. And then E, F, D, E, F are replaced with 1. Okay, you can see the last row, F, E, D columns are replaced with 1. Okay, so with this we go for the K-maps. Why are K maps required? We know we should end the problem with the implementation, okay, of logical diagram. For that we need K maps. That's what I've given there as a sentence. K maps are necessary to implement or realize the logic diagram. So how to do the K maps? We are all very familiar with this. We have come to the end of digital systems. Still I will explain. There are three variables. That is, I have named the present state as F, next state as F plus output Z. We know that already. 0, 0, 0, 1, 1, 1, 1, 0 are the inputs X, Y. And so there are three inputs, present state, next inputs X, Y. So we are taking a 2 power 3 is equal to 8 cell K map, 3 variable K map. And now mark all the values. How do you mark it? Here we should be very careful. F is 0. In the next state, the next state is 0, output is 0. Okay, you can see here 0 for the values of 0, 0, 0. The next state is 0. So you should mark here for the values of 0, 0, 0. The output is next state is 0. Okay, so to make you understand in a precise way, the first one is the next state, next value is the output. Here we have two K maps, one for the next state, another one for the output. So take all the first values 0, 0, 1, 0 and write it in the K map 0, 0, 1, 0. Okay, and next 1, 0, 1, 1, write it below 1, 0, 1, 1. Okay, similarly for the outputs, see the second values 0, 0, for a dash put a don't care 0. Okay, 0, 0, don't care 0. See here 0, 0, don't care 0. And then 1, don't care 1, 1. 1, don't care 1, 1. So the realization for next state F plus and Z, the output is done. Now you form the groups and you form the Boolean expressions from that. It is very simple. You know that. It's easy from the diagram. One more thing I want to remind you. While we did the state diagram from the C, I explained it as 0, 0, but I wrote it in the first slide as 1, 0. I have corrected it. Just take a note about it. The last step is the implementation. With these Boolean expressions, we have done the implementation. X, Y, it is an AND operation between them. So X, Y is given to an and then F, Y bar. So we have taken a NOT gate input to the second and with the F, the both of them are ART. So our R function is implemented to get your next state F plus, and Z is equal to F, that is the second expression. So what is the application of the asynchronous sequential circuit? They are useful when circuit system must respond quickly without waiting for a clock. So with this design gets over, and one or two definitions I would like to give you so that it will help you to attend the 2-mark question. We have seen the notes for primitive flow table. K maps, it is already there for you. And state reduction, I haven't written that on the board. So let me tell you that once a state diagram is drawn, it should be checked if any redundant states are there and should be removed. This will help us to avoid extra circuitry, extra space or area and the hardware. Okay, so this is called a state reduction. And what is state assignment? We have assigned A, B, C, D, E, F alphabets in the state diagram. Do you remember the first when we did at the beginning of this answer? What is that? The state assignment is assignment of binary codes to the states. Example, if there are 3 states, only 3 then state assignments can be done as A equal to 0, 0, B is equal to 0, 1, C is equal to 1, 0. If there are 4 states, then 0, 0, 0, 1, 1, 0, 1, 1 can be called as A, B, C, D. So I think this answer is clear to you. If you have any doubts, please post it in the comment section. I hope you like this video. Thank you.